Greetings, students. So today we are going to do a review over chapter 9. So we're going to have some review notes where I'll summarize the things that we've learned about sequences and series. So first of all, let's remember what it means to be a sequence. And a sequence is just a list of numbers. And then series is the sum of the numbers in a sequence. Now, we have two major types of uh, sequences, and therefore series, and they're called arithmetic and geometric. So here are some examples. So if we have a common difference, so the example on the left, so for example, we have 4 to 6, you add 2, 6 to 8, you add 2, and so on, you add 2 every time. So if that's the case, then this is going to be the arithmetic sequence, sequence. Now, we sometimes have see arithmetic sequence in the sigma notation. And in the sigma notation, remember that, and that makes it a series, meaning that it's a sum. So remember that a sigma notation is right here represents sum. And inside of the sigma, we have the expression that gives us the terms in the sequence. And please notice that these expressions are linear. So notice that this is a linear expression. So that's how we know that we're going to have an arithmetic series. So this is an example. We have 2x plus 1, which is basically mx plus b form. So this is linear, and therefore this is going to be arithmetic series. Okay. Now, then we have on the right here, we have an example where we don't have a common difference, we have a common ratio. And by looking at this, we can see that we are multiplying by 2 every time. So sometimes they're pretty easy to spot. Like you can see the pattern fairly easily, like in these two examples. However, if you cannot see it so easily, keep in mind that the common difference, remember it's denoted D, you can find it by taking your second term, so a sub 2 minus a sub 1, and then checking whether that common difference works for every term. So in this case, we would have had 6 minus 4, which is 2, and then we'll see is adding positive 2 every time works. In case of common ratio, well, common ratio means it's a division, so you would divide the second term by the first one, and then you see does this ratio works every time for the future terms. So in this case, it would have been 8 divided by 4, which is 2, and now we're checking does multiplying by 2 works every time. Now, once again, this is mainly needed when your common ratio or common difference is not as easy to spot as in these examples. Now, so whenever you have a common ratio, it's called an geometric sequence. And if we're looking at it in the sigma notation, then we recognize that it's going to be geometric by looking at the expression for the nth term, and if it's exponential, then it means that it's geometric. So if it's an exponential form, then it's a geometric series. So Therefore, we see arithmetic and geometric sequences and series. Now, the reason why we're focusing on these two, because there are many other types of sequences and series. Some of them have names and formulas, some of them don't. But the reason why we are focusing on these two is because these two we do have formulas for. So please remember that for arithmetic sequence, we have the nth term formula, which is right here. And this is the one that I usually use. However, if you simplify this formula, then it becomes this type. So I will bring this up again in our examples, but I usually don't use this formula. However, it's basically your mx plus b form. So remember, we talked about how arithmetic sequences are have linear expressions, make linear equations. So this is your d is common difference is the same thing as your slope. So this is really mx plus b form, and this c is what we call the zeroth term. So this is your a sub 0. And I will show an example of what that all means a little bit later. And then we have also summation formula. And the summation formula is this one right here. And this is the one where we talked about Carl Friedrich Gauss, where you basically add your first and your last terms, because they always produce the same sum, but then because you pair them, you multiply it by half of the terms. So you take all of the terms that you have, divide them by 2, because you pair them, and you perform that multiplication. And then we also have formulas for geometric sequences and series. Now, for as far as the sequences are concerned, it's pretty straightforward. It's this formula right here. Okay, so it's your first term times the common ratio to the power n minus 1. But when we talk about summation, then we have to be careful, because we can have two different sums. We can have a finite sum, and finite sum means that we adding the finite number of terms. So we stop at some point. So if we adding terms from 1 to 100, then we can use this formula right here. So this would be a finite sum. And notice the finite sum has n in it, because we do know how many terms we're adding. But then there is also something called the infinite sum. Oh yeah, by the way, finite sum is also sometimes called partial. So sometimes on your assignments, you might see something that says find the partial sum. Well, if it says find the partial sum, that means find the finite sum. But then there's also infinite sum. And infinite sum means that we add infinitely many terms. And here things get a bit trickier, because if you add infinitely many terms, infinitely many numbers, sometimes the logic tells us, well, if we add infinitely many numbers, then we just never get the full sum, because you add a million or more than billions of numbers, therefore they will you continue adding them and the sum continues increasing. But that's not necessarily the case. Then, because if our common ratio is between 0 and 1, that means that our terms become smaller and smaller, and therefore our sum converges. Converges means it approaches some number, and therefore we can actually use a formula to find what the sum converges to. And this is the formula right here. Notice in this formula there is no n, because we don't add any particular number of terms, we're adding infinitely many of them. And once again, this sum can be found by this formula. Now, something for you to think about is these formulas are actually related. So think about how are these formulas related on your own, and we can maybe discuss that in class at some point. Now, if your common ratio is greater than 1, that means that your terms keep increasing over and over, so you are adding bigger and bigger numbers. And if that's the case, then our sum diverges, meaning that it approaches to either positive infinity or negative infinity, which really depends on whether you're adding positive or negative numbers. If you're adding infinitely many positive numbers, then of course you will be approaching positive infinity. If you're adding infinitely many negative numbers, you'll be approaching negative infinity. Now, you don't need to tell me which infinity we're approaching. You only need to tell me whether, if this is the case, then you just need to tell me that the sum diverges. So these are the formulas that we've learned. And you do need to have these formulas memorized for the test. So please make sure that you do. They will not be provided for you. Now let's do some examples, and we have different examples of different kinds. Okay, so first example, write an equation for the nth term of the given series. Okay, so since we're writing an equation for the nth term of the series, we need first of all to decide, well, what kind of, not series, sequence. We need to decide what kind of a sequence we have. So we're looking at the sequence and we're saying, is there a common difference or is there a common ratio that we have? Well, if we look at this, from 5 to 3, it looks like we're subtracting 2. Then from 3 to 1, we're also subtracting 2, and so on. So in this case, it appears that we're subtracting 2 every time, or once again, you can try this by taking your second term minus the first. So that would be 3 minus 5, which is negative 2. That is a common difference. And then you check, does it work every time? And in this case, it does. So since we are subtracting the same number every time, that means that this is arithmetic sequence. Now, knowing that this is arithmetic means that we need to write an equation of the nth term. That means that we can use the formula a sub n equals a sub 1 plus d times n minus 1. Now, in this formula, we need to know what is our a sub 1, we need to know what is our d, common difference, and then n will stay as n. Okay, so in this case, our a sub 1 is the first term. So if we're looking the first term, that's 5. D, we already discussed that our common difference is negative 2. And once again, n is not going to be anything. We can just say n will be n because we're looking for the formula for the nth term. And now we're going to substitute everything in. Therefore, a sub n equals 5 plus negative 2 times n minus 1. But you do need to simplify this expression, okay? So if you leave your answer like this, I will not count this completely done. You have to simplify it by distributing negative 2 inside. So we have 5 plus negative 2n plus 2. And then combining your like terms, 5 and positive 2. And therefore, we get negative 2n plus 7. And that is your nth term formula. Now notice, so we can say a sub n equals negative 2n plus 7. Now keep in mind that this nth term formula, this right here, is that form dn plus c. The one that we've talked about before, the one that I usually don't use. And that c term, which in this case is 7, is your zeroth term. And what we mean by the 7 being the zeroth term is that if we're looking at the sequence and we go back, and by going back, instead of subtracting 2, since we're going backwards, we're adding 2, well, 5 plus 2 will give us 7. So that is our a sub 0. It's the zeroth term. So in reality, you could have found this formula without using the original formula that I wrote out. Without using this formula right here, you could have just said, okay, we know the common difference, and if I use the common difference, I can go backwards to find the zeroth term, and therefore I can write down this formula. So you can do it like this. I don't like doing it this way. I like a more methodic way, but that's really up to you. But the point is, if you're writing an equation of the nth term formula, you do need to simplify it. Okay, let's look at the next example. And here we need to find the sum of the series. So finding the sum means that we need to add them all together. And here we first of all need to decide, well, what kind of a sum is this? So we're looking at our sum, and we're going from 5 to 3. And from 5 to 3 means that we're subtracting 2. From 3 to 1, subtracting 2, and so on. So this is, once again, arithmetic. But now it is series. Okay, so since it's arithmetic series, meaning that we need to find the sum, we're going to use the S sub n formula. Now, in this formula, just like with everything else, we have the formula. Let's write out our terms. So we need to know a sub 1, a sub n, and then we need to know n. In this case, n does have to be a number because we're finding the sum, therefore we're finding the actual numerical value. Okay, well, a sub 1, pretty straightforward. That's our very first term. That's a sub 1. So a sub 1 is 5. Now, a sub n, we don't know n right now, but a sub n usually signifies the last term, so that would be our negative 33. That's your a sub n. Now, n is how many terms we have. Now, if we look at this series, we could try to count how many terms there are as we continue the pattern until negative 33, but that could be a bit complicated, so we actually need to find n first. And to find n, we're going to use the a sub n formula, which is this one right here. Or, since this is really the same sequence as what we've done in example 1, we can actually go and use this simplified form. So it doesn't really matter which one we use. I'm just going to stick with what I wrote earlier. I think that would be just more straightforward. So keep in mind, we need to find n, which means that we really have everything else, which we do. We know a sub n, which is negative 33. We know a sub 1, which is 5. We do know d, which is negative 2. And n is the only thing we don't know, and we can solve for it because it's the only unknown. So from here, we're solving this linear equation. You've solved those in algebra 1. You can distribute negative 2 inside. So you have negative 2n plus 2. Combine your like terms. So you have negative 2n plus 7. So once again, notice it's really what we found earlier. So we could have just started from that point. But, you know, sometimes they don't scaffold like this. That's why I'm doing it from the beginning. And now we're solving this two-step equation. So of course, subtract 7 and then divide by negative 2. So we have negative 40 equals negative 2n, and then divide by negative 2. And therefore we get 20 is equal to n. Now keep in mind, your n can never be decimal or negative because n is how many terms you have. The number of terms is always going to be a positive whole number. So if you've got n being a negative number or a decimal answer, you did something wrong. It can never be that. It always has to be a whole number. So it turns out that if you that our negative 33 is the 20th term, so it would have taken us a while if we tried to continue the pattern. Okay, now knowing all of the terms, now it's just application of the formula. So S sub 20, now we can say that we're adding the first 20 terms, and that would be 20 divided by 2 times 5 plus negative 33, and then we calculate this result. Well, 5 plus negative 33 plus 5 is negative 28 times 10 is negative 280, if I'm not mistaken. Good. I actually have a calculator here. So negative 33 plus 5. I just want to make sure. Yeah, negative 28 and then plus 10 would be negative 280. Okay, now, next one is we need to evaluate, and we're given the sigma notation. So if we're given a sigma notation, it is always a sum. Remember, sigma notation is sum, and sum is another name for series. So it is some kind of a series. We just need to decide which kind. Well, we're looking at the inside of our sigma notation and we see this expression, and this is a linear expression. And if it's a linear expression, that means that this is arithmetic. So it's arithmetic series. So knowing that this is arithmetic series, that means that we can use the summation formula or the series formula for arithmetic series, which is this formula right here, the same formula as what we've used a minute ago in the previous example. Now, to use this formula, just like before, we have to know first term, we need to know the last term, and we need to know how many terms there are. But these things we have to get from this sigma notation. Now, the first term. The first term always happens when we take the bottom number, so n equals 4 in this case, and we substitute it for n. So your first term would be 5 times 4 minus 2. So notice, very importantly, you don't, this number right here is not 1, it is whatever we start with. So in this case, we're starting with 4. Okay, so you calculate this, so it's 20 minus 2 is 18. Then a sub n, that's your last term. Want to find the last term, you take the top number and you substitute the top number in for n. And that gives you the last term. So 5 times 20 minus 2. So 5 times 20 is 100, and 100 minus 2 is 98. And now n. N is how many terms there are. Now, sometimes it's confusing because we see n at the bottom here and we see this n. Now, those are two different n's. That's why a lot of times instead of n, we're using a different variable there at the bottom, like I. But those are actually different things. So your n is how many terms there are total. And to find the total number of terms, you take the top number in the sigma notation, which is 20. You subtract the bottom number, which is 4. But if you do that, you are not counting your very first term. So therefore, you have to add 1 at the end. So 20 minus 4 is 16, plus 1 is 17. So there are 17 terms total. So having all of these numbers, we're going to substitute them into our summation formula, and then we're done. So it's S sub 17. So that means that we're adding 17 terms. And then it's going to be 17 divided by 2 times 18 plus 98. And then we just calculate this result. Oops. So we calculate this and we get 986 as the final result. All right, let's continue on. We have to find another sum here. And here, once again, sum means series. We need to determine what kind of series this is. Well, if we look at this pattern, okay, well, 2 plus 4 is 6. But then if I add 4 to 6, we do not get 18. So that is not going to be arithmetic. So other options, well, maybe it is geometric. To go from 2 to 6, we multiply by 3, and then go from 6 to 18, we also multiply by 3. So it seems like we're multiplying by the same value every single time. Therefore, this is going to be geometric series. Now, remember, if it's geometric series, we also have to be careful, and we need to determine, is it finite or infinite? Well, now, in this case, we stop at this big number at 118,098. Therefore, it is finite geometric series. And if it's a finite geometric series, we're using this formula right here. A sub 1 times 1 minus r to the power n divided by 1 minus r. Okay, well, to use this formula, we have to know a sub 1, we need to know common ratio r, and we need to know n, which is how many terms there are. A sub 1, once again, is your very first term. So that is going to be 2. Common ratio r is what you multiply by. In this case, it is 3. D, it's R. So this is going to be 3. Now n is how many terms we have, and once again, we do not know what is the number of this very last term. We have no idea what it is. We can try to continue the pattern, but once again, we're going to 118,098, so that's probably going to take a while. So we have to find our n. And to find n, we have to use the geometric a sub n formula, which is this one right here. Now, for this formula, let's see, we have a sub n, which is 118,098. We know a sub 1, which is 2, and we know common ratio, which is 3. The only thing we don't know is n. But here we have to solve the exponential equation. Well, to solve the exponential equation, remember, first of all, you have to get rid of this 2. So we have to divide everything by 2. And we get 59,048. And now from here, one of the ways we can continue with this is we can take the log of both sides. So we'll have logarithm of 59,048 equals logarithm of 3 to the power n minus 1. Remember, the whole point of taking the logarithm is so we can use the power property and bring this power down. So then we'll end up with log of 59,048 equals n minus 1 times logarithm of 3. We can divide everything by log of 3. And so we have logarithm of 59,048 divided by log of 3. And something is wrong. Oh, it's 49, not 48, my bad. I'll fix that in there in a second. Okay, so if it's 49, then we get just 10. Okay, that makes much more sense. So let me fix this. So this would be plus 49. Okay, so we get 10 equals n minus 1, and then we just add 1 to the other side. So therefore, n equals 11. So notice that once again that I knew that my answer was incorrect originally when I used the calculator because my answer was decimal. And your n, which is the number of terms you're adding, can never be decimal or negative. It always has to be a positive whole number. So that's how I knew that that was a mistake. So, but now here we know that n is 11. And at this point, it is a direct application of the formula. So we're adding 11 terms. And then it's 2 times 1 minus 3 to the power 11 divided by 1 minus 3. And you can just type the whole thing in your calculator, especially with the yellow ones. It would be pretty simple. So this one, for example, doesn't do a fraction button like that, but we can still do our best. So 2 times 1 minus 3 to the power 11. Okay, and we get this result, and then we're going to divide this by 1 minus 3, which is negative 2. And therefore we get 177,146. 177,146. And that will be our final answer. Okay, let's continue. And now we have a sigma notation. So we have to evaluate the expression using sigma notation. And remember, sigma notation means sum. So therefore, we have some kind of a series. And now here we, once again, have, since it's series, we have to determine what type of series this is. Well, by looking at this expression right here, we see that this is exponential. It's an exponential expression. And if an expression is exponential, that means it's geometric. So it's geometric series. Moreover, we can see that the top value is infinity. So it's not just any geometric series, it is infinite. So we have not just series, but more specifically, infinite geometric series. Now, if it is infinite, here, before we go straight and diving into the formula, we have to check what our R is equal to. Because if R is greater than 1, then the series diverge and there is nothing that we need to do there. So, our R is always the base of the exponent. So our exponent is n, and therefore the base is 2/3. So our R is 2/3. Now 2/3 is clearly less than 1, and since our R in the infinite series is less than 1, then the series converge. And converge means that they do approach some value, therefore we can find the sum using this formula. Okay, now knowing the formula, we need to know what's our a sub 1, and we need to know R. Notice that the only two parameters in this formula. Well, to find a sub 1, we take the bottom number, which is 4, and we substitute it instead of n. So taking our 4, substitute it in for n. So it's going to be 3 times 2/3 to the power 4. And we can calculate this. So let's see what we're going to get. 3 times 2/3 to the power 4. And we get this decimal. It's better probably to write this as a fraction. So let me do this just by hand, because the decimal, if we round it, it will give us an inaccurate answer, and we want an accurate answer. So let's see what we're going to have. So it's going to be 3 times 2/3 to the power 4 means it's 2 to the power 4, which is 16, and 3 to the power 4, which is 81. And therefore we got 3 times 16 divided by 81, and then we can reduce this. So it's going to become 16 over 27. So we're going to leave this as a fraction. Once again, with the yellow calculators, they will calculate this as a fraction for you, or you can convert it. But here we had to do it by hand. Now our R, we already know that is 2/3. So from here, we can use our formula. So S is equal, notice there is no n here because we're adding infinite number of terms. So S is equal to 16 over 27 divided by 1 minus 2/3. Once again, your yellow calculators can do this calculation fairly easily and give you a decimal, a proper fraction answer, but here we have to do it by hand. So it's 16 over 27, 1 minus 2/3 is 1/3. Then when we're dividing two fractions, that means that we take the denominator and flip and multiply. And here we can also reduce our fraction a little bit to make it easier. And therefore it looks like we're going to end up with 16 divided by 9. Now you can convert the 16 divided by 9 into a decimal if you really want to, which is 1.7 repeating. So doesn't matter which answer you produce. In this case, fraction answer is more accurate. I prefer those, but it doesn't really matter. So, but please be careful whenever you have infinite geometric series. First of all, you need to confirm, is it going to be converging or diverging? All right, let's look at the next example. We have another sigma notation. And by just looking at this, we can see that it is going to be infinite series. And by looking at the inside, we once again see that this is an exponential expression, which means it is geometric series. And it is also, we already decided, it's going to be infinite. So once again, if it is infinite geometric series, we need to determine our R first. and our r, once again, is the base of the power, which is 3 over 2. Now 3 over 2, or 1.5, is clearly greater than 1. And if our common ratio is greater than 1 in the infinite series, then our series diverge. That's it. There's nothing else that we can do here because the sum of these numbers will basically go to positive infinity. You don't need to go into those details. It's enough for you to just say that the series diverge. Now, before we continue to the next example, please keep in mind that we're checking whether our common ratio is greater than 1 or less than 1 only for the infinite series. So if we go back to example 4, notice the common ratio here is 3. But notice I'm not comparing my 3 to 1, whether it's greater or less than 1, because it is finite series. It's finite series. And finite series always converge because you can always find the answer when you add finite number of terms. So we only check whether R is greater than 1 or less than 1 if it is infinite series. So please be careful about that. All right, next few things. We want, for number 7, we want to write our sum in the sigma notation. Now, sigma notation looks like this. And in the sigma notation, at the bottom, you can use n if you want to. We're always going to start with 1. At the top, we're going to put the number of terms. Or number of the last term. If you start with 1, they're the same things. If you don't start with 1, then the number of the last term and the total number of terms, that's going to be a little bit different. So that's why I always suggest to start with 1 at the bottom. And then in the middle, this is going to be your a sub n formula. Okay, so we have 3 pieces. We have where we start, and we always should start with 1. In the middle goes our a sub n formula, the formula that will produce every single one of these terms. And at the top is the total number of terms, or really the number of the last term. Okay, so those are the 3 pieces. Well, the first piece we already know, n equals 1. So we're starting with 1. Now, let's figure out the a sub n formula. So to figure out the formula, we're looking at the pattern. Now, in this pattern, we seeing that we're going from 10 to 5, but then from 5 to 2.5. So it doesn't seem that we're subtracting the same number. Let's check for the common ratio. Well, the common ratio would be 5 divided, remember, it's going to be a sub 2 divided by a sub 1. So in this case, it's 5 divided by 10, which is 1/2. So let's see. 10 times 1/2 does give us 5. 5 times 1/2, well, it does give us 2.5. 2.5 times 1/2 does give us 1.25. So it seems that we do have a common ratio, which means this is geometric. Now notice, I'm not trying to evaluate this, so I don't actually care whether it's finite or infinite or anything like that. I'm writing a sigma notation. So I do need to know that it's geometric, because knowing that it's geometric, we can find the a sub n formula by using a sub 1 times r to the power n minus 1. And in this case, we do know a sub 1. That's our very first term. We do know r. We just calculated this. That's 1/2 n minus 1. And that is the expression that we're going to put in the middle of our sigma notation. So here, we already know that n equals 1. And then in the middle, our expression would be 10 times 1/2 to the power n minus 1. All we have left to do is figure out what number goes on top, how many terms there are. So we need to find n. Well, to find n, we're using the a sub n formula. We've done this a couple of times before. Now we already know a lot of things here. We know that a sub n is 0.078125, and then it's equal to 10 times 1/2 to the power n minus 1. Now we need to solve this exponential equation, and so let's do this. Remember, you always want to get rid of your leading coefficient first, so you have to divide by 10 first. And when we divide by 10, now it's going to become 0.00788125 equals 1/2 to the power n minus 1. And we, of course, have to take a log of both sides. And so on. So log of 0.00788125 equals, I'm going to speed this up a little bit so we can bring the power down, n minus 1. And that's going to be log of 1/2. And then we're dividing by the log of 1/2 on both sides. Okay, and we can use calculator to do so. So log of 0.00788125 divided by log of 0.5 or 1/2. Oops. And we just get 7. Yeah, all of that to just get 7. So we get 7 equals n minus 1, and then you add 1, of course, so therefore you get 8 equals n. So we know that at the very top, we're going to put 8. And that's it. That is our sigma notation. Now, keep in mind, you can always check your answer. And to check your answer in the sigma notation, it's very simple. You can substitute 1 in for n and calculate what you're going to have. And you should get the very first term, which is 10. And you can do this and you will see that you will get that. And then you can also substitute 8 in for n. And what you should get is the very last term. So you can try this and I guarantee you will get that decimal answer. So, but that's one of the ways you can check your answer for the sigma notation. But otherwise, that's what it is. Okay, let's look at another sum that we once again need to write in the sigma notation. So once again, we're going to put the a sub n formula in the middle. At the bottom, we're always going to start with 1. And at the top, we need to know what's the last term. Okay, so by looking at this, we might be able to notice that we are subtracting 5 every time. And since we're subtracting 5 every time now, this is arithmetic. So this is arithmetic series. So knowing that this is arithmetic series, to find our a sub n formula, we're going to use a sub n equals a sub 1 plus d times n minus 1. And here, keep in mind, we're not going to put anything for a sub n because we'll want to find the formula. We want to basically find this portion right here. And for this portion, we know pretty much everything that we need to know. We know a sub 1, which is 10. We know d, which is -5. And then it's n minus 1. We do need to simplify this. So we distribute this -5 inside. Combine like terms. We get -5n plus 15. So that is your formula that will produce every single term. So we are almost done. We have 2 out of the 3 pieces that we need. So you can put this in the parentheses if you want to show that the whole thing is inside of the sigma notation, but that's okay. And now we need to find the value of the last term. Well, to find the on the number of the last term. Well, we know that the last term is -135, so we can use this found formula to solve for n. So find n. And to do that, we're going to have negative 135 equals negative 5n plus 15. And that's just a basic two-step equation. So we can subtract 15. We'll get negative 150 equals negative 5n. And then divide by negative 5. And therefore we'll get n is equal to 30. Notice, once again, has to be a positive whole number. So here we're dividing negative by negative, and we do get a positive. So we get 30. And therefore, that is our sigma notation. And once again, you can check your answer by substituting the bottom number in and seeing if you're going to get your first term. So if we substitute 1 in for n, we should get 10, and we will. And you can substitute 30 in for n, and we should get negative 135, and we will get negative 135. So that is our correct sigma notation. Okay, the last thing that we're going to review today is the recursion formula. So write the first 4 terms of the sequence defined by recursion formula. Remember, recursion formula uses previous terms to find the future ones. So we have the first term already. We know the second term already. We do need to find the first 4, so we just really need to find the third and the fourth terms. Now, here we have a sub n minus, so the recursion formula is a sub n equals 10 plus a sub n minus 2 times 4 plus a sub n minus 1. So n minus 2 means 2 terms back. And a sub n minus 1 means 1 term back. Okay, so if we're talking about a sub 3, that means we're going to have 10 plus. Now, a sub n minus 2, well, this right here is your n. So n minus 2 would be a sub 1. Or once again, it is 2 terms back. So if we're talking about the third term, 2 terms back will be the first term. Times 4 plus, well, then a sub n minus 1 will be a sub 2. I highly recommend that you write out your expression using a's first and only then start substituting the numbers. So now it's much easier because we see a sub 1, well, we know that value, that's 3, and a sub 2, we know that value, that's 5. And therefore, it's going to be 10 plus 3 times 4 plus 5. And you can use your calculator to do this. Just make sure you don't make any silly arithmetic mistakes. This is, of course, is 13. This is, of course, is 9. So you multiply, and this is multiplication. So you multiply 13 times 9, which is 117. If I'm not mistaken, 93 times 9 is 27. Yeah, pretty sure. So let's double check just to make sure. So 13 times 9, 117. Okay, cool. Now we need to find a sub 4, so we do the same thing. 10 plus, now it is 10 plus n minus 2, so 2 terms back. So from 4, 2 terms back would be a sub 2. And then 4 plus a sub n minus 1, so 1 term back, which would become a sub 3. Okay, well, let's see what we have. We know a sub 2, that's 5. And we do know a sub 3, which we just found to be 117. Therefore, it's going to be 10 plus 5 times 4 plus 117. And here we'll just use a calculator. So 10 plus 5 times 4 plus 117. And we get 1,815. So we have our first 4 terms. They are 3, 5, 117, and 1,815. So these are the first 4 terms as we were asked to find, but in reality, we just had to find these two. Okay, so this is the summary of our chapter 9. I hope it will help you to study for your test. So good luck.